Hey there, it's Shannon Myers coming at you live from San Diego, California. It's a beautiful day today, and even more so because we will learn about Gauss-Jordan Elimination. I know that a lot of you might be thinking, why the heck do we need to know how to do these things by hand? The reason for this is that later on in linear algebra, you may not have real number entries. There might be, there's more abstract things going on. So if you understand how to manipulate matrices and do row operations and all that kind of stuff, then you'll be ahead of the game. All right? So here we go. Let's do our math stretches so that we can interpret the augmented. So notice that I bolded the word augmented matrices. The augmented matrices might have a line. They might have a dashed line, or they may have no line at all, like here, but you're told it's an augmented matrix. So you have to always make sure you know what you're working with before you get started. All right, here we go. Pause the movie and interpret these to the best of your ability. And when you're done, go ahead and play the video again and you can see how you did. All right, good luck. Okay, let's see how you did. If you're ever in any doubt, the best thing to do is to just put this back into a system. This meaning we have 1, x1. We're just deciding what the variable is going to be notated as. Plus 0x2 plus 0x3 is equal to 8. 0x1 plus 1x2 plus 0x3 is equal to 7. And then 0x1 plus 0x2 plus 1x3 is equal to 5. So this is the equivalent system, okay? Well, of course, what do we get? We just get that x1 is equal to 8, x2 is equal to 7, and x3 is equal to 5. So we don't know why, this matrix was here, but we certainly know that the solution is a single ordered triple, and that ordered triple is 8, 7, 5. And what kind of system is this? Beautiful. It's going to be a consistent system. Cool so far? All right. There we go. Well, that looks kind of weird. Sorry. Now, what about this next one? I mean, how would we do this? How would we notate this next matrix? Well, again, put this into a system. You know it's augmented, so if it makes you feel better, go ahead and draw the line there. And what do we have? Well, we can say that this is equivalent to 1x1 minus 1x2 plus 0x3 is 0, right? Is equal to -2. And then 0x1 is just 0. 1x2 plus 3x3 is equal to 11. Uh-oh, what kind of system is this? It's a dependent system, isn't it? So it's still consistent, but it's going to have infinitely many solutions. So here we go. Let's come over here, and in the first equation, why don't we isolate x1? So here we have x1 will equal to positive x2 minus 2. And for the second equation, let's go ahead and isolate x2. So x2 is going to equal to what? Awesome. 11 minus 3x3. Now, can't we go ahead and simplify this a little bit, because this meaning the x1, we know that x2 is equal to this here, right? And we want to have the least amount of parameters as possible. So I am going to say x1 is going to equal to 11 minus 3x3 minus 2. The 11 minus 3x3 is substituting in for x2. And this in turn will be equivalent to, beautiful, 9 minus x3. I'm sorry, 9 minus 3x3. Cool? Now let's parameterize. The only parameter we'll have is x3. So why don't we let x3 equal to t? And so that means that x1 will equal to 9 minus 3t. And x2 will equal to 11 minus 3t. And our solution for this system will be 9 minus 3t, 11 minus 3t, and t, such that, what is t? Beautiful. T is an element of the real numbers. Groovy? All right, so here we go. Next up. Oh, and this, by the way, is a consistent system. It has infinitely many solutions. But it has dependent equations. This one here had independent equations. All right, so next up, what do we have? Part C gives us another dependent system, right? So what will we have? We'll have 1x1 plus 2x2. And again, if you need to, draw the little line here so you can see the augmentation here. And then 0x3, so we don't have to represent x3 in the first equation. And then plus 4x4 is equal to 3. Then, what's the next line? 0x1 is 0 plus 1x2. Again, we have 0x3s, but we can't just ignore them. I mean, that just because x3, there's no x3s, that the x3s zero out in both equations, you're still going to have to parameterize it because it was in there, right? It's not like a row of zeros that we can just get rid of. So here we end up with x2 plus 7x4 is equal to 0. So if I isolate x1, x1 will be equivalent to, actually, new line here. So x1 will equal to 3 minus 2x2 minus 4x4. And then x2, I'm isolating in the next one, and that's going to equal to negative 7x4. So again, we've got x2 as part of x1. So remember how last time in for x2, we want to plug in, this negative 7x4. So x1 will equal to 3 minus 2 times negative 7x4 minus 4x4, which in turn gives us 3. That would be positive 14x4 minus 4x4, so we'll get plus 10x4. All right, so how many parameters are we going to need? We're just going to need one for x3 and one for x4. So let's do it. We'll let x3 equal to s and x4 equal to t. So this will give us, for the first one, x1, I'll just put it up here, this in turn is going to give us 3 plus 10t. Are we okay there? All I did is I replaced the x4 with the t. And then x2 is going to be negative 7t. Same reason. Oops. So this time we'll have an ordered 4-tuple, and this will be x1 ended up being 3 plus 10t, x2 is negative 7t, x3 is s, and x4 is t. So how do we describe s and t? Beautiful. S and t are elements of the real numbers. Cool, cool? All right. Okay, so next up we'll look at elementary row operations now that you're all warmed up. And so here, this is where we'll start doing these wonderful matrices, row reducing them by hand. But it's very useful. It helps you understand all the, definitions and theorems in the course and the proofs for them. So it turns out that you can add 2 rows. So these are going to be really just about the same as systems of equations, except we add a 4th one. You can multiply a row by a non-zero constant. You can add a multiple of a row to another row. And you can interchange, we usually just say swap, any 2 rows, or columns, actually. All of these work for columns as well. All right, so first definition, row echelon form and reduced row echelon form. A matrix in row echelon form, which we usually abbreviate as REF, has the following properties. Any rows consisting entirely of zeros, the computer system swaps them so that they're at the bottom. Okay, so and they do it automatically. You would do it as a swap. All right, but typically the way that you row reduce by hand, you end up with it that way anyway. Okay, but not necessarily. So you would just put any row of zeros would be at the bottom of the matrix. For each row that does not consist entirely of zeros, the first non-zero entry is 1. This is called a leading 1. It's also called a pivot. For 2 successive non-zero rows, the leading one in the higher row is farther to the left than the leading one in the lower row. A matrix in row echelon form is in reduced row echelon form. So this abbreviation is RREF in the computer programming and in the GraphNCalculator. So it's in RREF form when every column that has a leading one has zeros in every position above and below its leading one. So here we go. Determine which of the following augmented matrices are in row echelon form. So what do you think? So always go back to your definition. Row echelon form, right? You would have, these are augmented matrices. So why don't we put the lines in here? So basically, the first one is actually the hardest. It is definitely in REF form, and that's really the only form it can go into, because it's dependent. We can't zero out the negative 1/2. Okay, but the answer is yes, because we were asked about whether these augmented matrices were in REF form. So what about B? Beautiful. You've got zeros here. That triangle of zeros will really help you. All right, so again, this is in REF, not RREF. Both of them are fine, but just so you know, that's the case. If it was in RREF form, you'd have all zeros here, okay? Now, what about C? No, why does this violate the definition? Because of these two rows, right? If they were swapped, you'd have row echelon form, right? Actually, the whole thing. If they were swapped, you'd have row echelon form, but they're not, so you don't. Doesn't follow the definition, so our answer is no. All right, so Gauss-Jordan elimination really simplifies the whole thing, okay? So the way to do it is you write the augmented matrix of the system of linear equations, and then you use elementary row operations to find an equivalent matrix in reduced row echelon form, the RREF. If it's not possible, that means it's dependent or inconsistent. Then you write the equivalent system of equations and back substitute. So it'd be an REF form, not RREF. And then you got to be able to interpret your results. So second example, solve the system using Gauss-Jordan elimination. So here we go. Name our matrix. Might as well name it B. And how do I translate this? Beautiful. I'll have 1, 1, -5, 3, 1, 0, -2, 1, and then 2, 1, actually -1, -1, and 0. Good so far? All right, so we've got this augmented matrix B. Well, now, what do you think we have to do? You know, you could swap. The sad thing is that I think what's going to happen is your 0 might go away anyway, and it might be a little bit frustrating. So I don't know. A lot of times it's sort of a waste of time to swap unless it's something that's very, very clearly helpful. In this case, the zero's in the middle. It's got numbers on the, it doesn't have zeros on either side of it. So I'm kind of thinking, let's just do this thing. All right. So what we want to do is there's an order that you go in. We want to get this lower triangle zeroed out. So you're going to do second row, first column first, third row, first column second, and then third row, second column third. And then if you kind of follow the same pattern when you go to the top, you do in the opposite order. The third column stuff happens first, and then the second column thing happens last. Okay? So, let's do it. Initially, what do you think we ought to do? Well, and just kind of trust me on this. I don't like putting a minus in between my row operations. I'd rather do this. I'd rather say -1 row 1 plus row 2, and this will give us a new row 2. I have a reason for that, and it will come up. It will come up later, as I think, especially when we're dealing with determinants. All right, so just kind of take my advice on that. So here, if I do negative row 1, it's going to make an opposite sign of everything. So I'll have -1 plus 1. Oh, actually, let me rewrite the rows that won't change, which will be the first and third on this step. And then we'll write in purple the new row. So -1 plus 1 is 0. -1 plus 0 is -1. -5 is +5. So 5 plus -2 is +3. -3 plus 1 is -2. So this is our new row 2. And this matrix is equivalent to matrix B. Cool? Okay, so now we want to get rid of the 2 that is in the third row, first column. So what do you think we ought to do? Awesome. -2 row 1 plus row 3 for a new row 3. So, rewriting rows 1 and 2 this time, because they'll be the ones that are unchanging. We will have, so if I multiply row 1 through by -2, let's see, we'll get -2 plus 2 is 0. -2 plus -1 is -3. -2 times -5 is +10. 10 plus -1 is 9. And then we'll have what? -6 plus 0 is -6. Cool? Alrighty. Next up, what do you think? Well, if we do -3 row 2 plus row 3, we'll get a new row 3. So then we'll have 1, 1, -5, 3. 0, -1, 3, -2. All right, so now our new row 3 will be, we'll still have a 0 here. Notice that we have to use that row 2, so we don't, if we had used row 1, what would happen is you'd get a 1 there and it would be very circular and you'd be very sad. So, just do these in the order in this way and you'll be okay. All right, so then if I multiply -1 by -3, I get +3. Add -3, I get 0, like our plan was. Now, -3 times +3 is -9, and -9 plus 9 is 0. And then let's see, -3 times -2 is +6. 6 plus -6 is 0. So I ended up getting a row of zeros. Well, what does that mean? That means that this is a dependent system. Dependent system. So from this point on, just back, from what we have here, we just want to back substitute this into a system. So the equivalent system that we have here would be 1x1, yes, and then plus 1x2 minus 5x3 is equal to 3. Negative x2 plus 3x3 is equal to -2. So if I isolate x1 in the first equation, I will get 3 minus x2 plus 5x3. And if I isolate x2 with a little bit of algebra, what's going to happen? I will get +2, and then what? I'd be subtracting a 3x3, right? But then it would go positive, so I'd have +2 plus 3x3. So, again, what do you see? You've got x2 within x1. So simplifying x1 more, I can say x1 is equal to 3 minus 2 plus 3x3, and then plus 5x3, which in turn will equal to what? 3 minus 2 is 1, and -3x3 plus 5x3 is +2. So we would end up getting, I'll just write it as 2x3 plus 1, and x2 is still 2 plus 3x3. And if we now let, how many parameters do we have? We just have one parameter, right? And by the way, this was because we had x2 right here, and x2 is this. So if we let x3 equal to t, what's going to happen? Well, this one here is going to be 2t plus 1. x2 will be, I'll write it as 3t plus 2. And then we'll have our solution. And this is dependent, right, and consistent. So we'll have 2t plus 1, 3t plus 2t, that's an ordered triple, such that t belongs to the real numbers. And then this is a consistent system. And you need to know that wording, with dependent equations. All right. We good? Oh, and then this is for t. This is what I had put in. So x3, remember, was t, and so that's where we got the t here and the t here. Groovy. All right, so let's see what we've got coming up next. We have another example that we need to work on, so why don't you guys go ahead and pause the movie and try this one on your own and see how you do, okay? All right, you can do it, I know it. All right, let's see how you did. So if we let b equal to 5, negative 3, 2, 3, 2, 4, negative 1, 7, 1, negative 11, 4, 3, and just follow the same process, right? So here, I want to get rid of the 2 that I want to zero out the 2 that's in the second row, first column. So in order to make this happen, I need to multiply the top row by negative 2, and then add the bottom row the second row multiplied by 5. And this is going to give us a new row 2. So here we go. Rewriting the rows that aren't changing, so that'd be rows 1 and 3. All right, so our new row 2 is we'll get negative 10 plus 10 is 0 when we do those multiplications. And then we'll have positive 6 plus 20, so we'll get 26. And then negative 4 plus negative 5 will give us negative 9. And then negative 6 plus 35 will give us positive 29. All right. So next up, let's zero out the 1 that's in the third row and first column. So when we do this, we will have to what? I'll do negative row 1 plus 5 times row 3, and that'll give us a new row 3. So I'm rewriting the rows that won't be changing this time, and that's rows 1 and 2. So our new row 3 will end up with negative 5 plus 5 is 0, like we planned. And then we'll have positive 3 minus 55 will be negative 52. And then a negative 2 plus 20 will give us 18. And a negative 3 plus, let's see, what do we have? We'll have a negative 3 plus 15 will give us 12. Cool so far? Awesome. All right, so here we go. We're on to, I'm going to bring us up here. And actually, we can say what the row operation, well, I'll just bring us up here first. So our row operation, do you see that if we just double the second row, we can zero out the negative 52 that's in the third row, second column. So I need to say 2 row 2 plus row 3 for a new row 3. I'm changing just the third row, so I'm going to rewrite the first and second. All right, let's see what our new row 3 will be. So 2 times 0 is 0, and then plus 0 gives us 0 still, which is good. Then we're going to end up with 2 times 26 is 52 plus negative 52 zeros out, like we planned. Then we're going to have negative 18 plus 18, which zeroes out. This will be a weird one. And so at this point, it's either going to be dependent again or an inconsistent system. All right, so let's see what happens. So 2 times 29 is 58, and 58 plus 12 is what? Beautiful, 70. So this one, sometimes people, kind of confuse things a little bit. So here, this is going to be equivalent to the following system. We will have 5x1 minus 3x2 plus 2x3 is equal to 3. That's our first row. 0x1 is just 0. Actually, I'll write them this time since we have that weird row 3. And then plus 26x2 minus 9x3 equals 29. And then 0x1 plus 0x2 plus 0x3 is going to equal to 70. So when I simplify these again, what's going to happen? Well, the first one will be the same, as will the second. Well, second we'll simplify to get 26x2 minus 9x3 equals 29. And then the third one is basically going to be 0 on the left side and 70 on the right side. So what do you think about that? Is that true? Does 0 equal 70? Well, no, not unless you've been drinking, right? So here, what we've found is a contradiction. And in this case, the contradiction is going to tell us that we have an inconsistent system. So remember, you do just one or the other. So the empty set or, the null set represented as the 0 with the line through it, okay? This is an inconsistent system. And so we don't care really if if you've got, we might care, but it's an inconsistent system and it's going to have independent, I'll write it, with independent equations. So next up, and this is something that you're going to want to remember, definition of homogeneous systems of linear equations. So systems of equations in which each of the constant terms is 0 are called homogeneous. A homogeneous system of m equations and n variables has this following form. So sorry, I forgot to do some of the dots, but you basically have this format here, and go down like this too. So basically it's the same as we defined, a system of equations, except for instead of B1, B2, B3 that they're equal to, you have all zeros. So it turns out that homogeneous linear systems either have the trivial solution, which is x1 equals 0, x2 equals 0, x3 equals 0, etc. Let me write that down. Basically, it's just an ordered n-tuple at the origin. Or you can have infinitely many. You'll have something that's dependent. So what does this mean? It means that homogeneous systems are always, always, always consistent. Okay, so next up, let's look at this example. So solve the homogeneous linear system corresponding to the given coefficient matrix, okay? So this is not augmented, all right? So one thing that a person, could do if you wanted to is you could rewrite it with the augmented, and you have to know what homogeneous means, don't you, in order to do that. Homogeneous means that the constants are zeros. So here, whether you actually write that out or not, what's going to happen is you'll end up with the following system. If we call them x1, x2, x3, and x4, right? You'd have x1 is going to equal to 0, right? And then x2 plus x3 is going to equal to 0. But what can we do with this? Beautiful. x1 is just 0. It's good to go. But couldn't x2, so we'll keep that, x1 is 0, but x2 is equal to the opposite, or the negative, of x3, right? And if we were to let x3 equal to s, and don't forget about x4, you have to represent it, it would equal to t. That's going to mean that we'll have x1 is 0, x2 is negative s, x3 is positive s, and x4 is t. So our solution would be this ordered four-tuple, which is 0, negative s, s, and t, such that, beautiful, s and t are elements of the real numbers. And this is a consistent system with awesome dependent equations. Okay, so here we go, our very first theorem, all right? Theorem 1.1, the number of solutions of a homogeneous system. So every homogeneous system of linear equations is consistent, as we said before. If the system has fewer equations than variables, then it must have infinitely many solutions, all right? So now we're going to go ahead and go to polynomial curve fitting. Suppose endpoints in the xy plane represent a collection of data, right? And you are asked to find a polynomial function of degree n minus 1 whose graph passes through the specified points. This is called polynomial curve fitting. So it's not like linear regression, because linear regression finds the best fit line. What this one is doing is it's going to pass through the specified points. So they have to be on the polynomial, all right? So it is different. So if all x coordinates are distinct, then there is precisely one polynomial function of degree n minus 1 or less that fits the n points. To solve for the n coefficients. So we'll be solving for coefficients of some polynomial in x. What we need to do is substitute each of the endpoints into the polynomial function and obtain n linear equations in n variables. A0, A1, A2, all the way to A(n minus 1). So polynomials always allow for the constant term, right? So that's why you go to n minus 1, right? That's why the degree of the polynomial function is n minus 1, but you still have n variables. Cool, cool? Okay, so basically what happens is, sorry, these go on like this. What happens is you end up having, each of these as polynomials. So A0 plus A1 x1 plus A2 x1 squared plus ... plus an minus 1 x1 to the n minus 1 is equal to y1. So just notice what changes and what matches. So do you notice that the subscript on the a's matches the power on the x1? And that happens through the whole system, all right? So let's check out this next example. Determine the polynomial function whose graph passes through the points and graph the polynomial function showing the given points. So how do we know what our n is? Well, how many ordered pairs do we have? Beautiful, 3. So n equals 3 since we have 3 ordered pairs. Okay? So that means that n minus 1 is going to be beautiful, 2. All right. So in general, a polynomial in x is equal to some a0 plus a1x, and we are going to a degree of 2, so we'll have plus a2x squared. If we had 5 ordered pairs, we would have a 4th degree polynomial, okay? So, well, what have we been given? We've been given that our polynomial evaluated at 1 has an output of 8, right? That's from that first ordered pair. So if we input 1 into our polynomial, we get out 8. But how can I also write this? I can also write this, because remember I'm solving for coefficients, right? So I can also write this as a0, awesome, plus a1 times what? What am I plugging in for x? Great, I'm plugging in 1. And then plus a2 times 1 squared. So because I'm on this particular problem where I plugged in 1 for x, I plug in 1 for x all throughout, okay? All right, and that in turn is going to equal to what? a0 plus a1 plus a2. Okay, our polynomial evaluated at 3 has an output of, awesome, 26. So that'll be also equivalent to a0 plus a1 times 3 plus a2 times 3 squared. Again, we plugged in a 3, and when you plug in a 3, you get out 26. This is what was found by this data. Well, that's going to be equal to a0 plus 3 a1s plus 9 a2. And then we've got one more. our polynomial evaluated at 5 has an output of 60. So that's also going to equal a0 plus a1 times 5 plus a2 times 5 squared, or we would have a0 plus 5a1 plus 25a2. Okay, well, let's put this in a system. Let's clean it up a bit. So this is, just so you know where we got this. All right. So our system we're going to use the simplified coefficients. So we have a0, for our first one, we have a0 plus a1 plus a2, and then I'm going to put the y's on the other side, or the outputs on the other side, and that was equal to 8. So the second one is a0 plus 3a1 plus 9a2, and that was equal to 26. And then our third one will have a0 plus 5a1 plus 25a2, and that was equal to 60. Cool, cool? All right. So what would our matrix B end up looking like? Well, we'd have 1, 1, 1, 8, 1, 3, 9, 26, and then 1, 5, 25, 60. Cool so far? All right. So next up, we want to do our row operations, all right? So usually when I'm doing this stuff by hand, unless you're working with inverses, I just get the RAF form and then I back substitute, all right? So here we want to zero out the 1 that's located in the second row, first column. So in order to do that, we want to do negative row 1 plus row 2 for a new row 2. And that will give us, so what are we changing the second row? So we'll have the first and the third will remain the same. And our new second row will be what? Well, we'll have negative 1 plus 1 is 0. Negative 1 plus 3 is 2. Negative 1 plus 9 is 8. And negative 8 plus 26 is 18. Good, good? Alrighty, and then next up we want to zero out the beautiful, the 1 that's located in the third row, first column. So we'll do negative row 1 plus row 3 for a new row 3. Actually, okay, so that will give us, let's see, we're changing just the third one. So the first row and the second row will stay the same. A lot of 8s in this. And then we'll have a new third row. Okay, so negative 1 plus 1 is 0, like we planned. The next one will be negative 1 plus 5, so we'll have 4. Negative 1 plus 25 is 24. And negative 8 plus 60 is going to be 52. Cool, cool? Alrighty, so let's come up over here and see what we need to do next. So we want to get rid of we want to zero out the 4 that is in the third row and second column. So I'll just go ahead and do negative 2 row 2 plus row 3 for a new row 3. And so now the first and second rows again will stay the same. have, let's see, so we'll end up with 0 plus 0 is 0. And then negative 4 plus 4 is 0. Negative 16 plus 24 is going to be what? Good, positive 8. And then what do we have? We have 18 times 2 is times negative 2 is negative 36. So negative 36 plus 52 is going to be beautiful 16. All right, so here let's just put this back into well, if you want to get it into reduced row echelon form, we would do a couple more things. We would say negative 1/2 times row 2 for a new row 2. All right, so that'll give us 1, 1, 1, 8, 0, 1, 4, 9. Oh, I should have done that in the other color, right? And then that third row would be the same. And then the next step would be, we would want to get a 1 where that 8 is. So we'd say 1/8 times row 3 for a new row 3. And that will give us 1, 1, 1, 8, 0, 1, 4, 9. And our new row 3 is going to be 0, 0, 1, and 2. So now it's just a matter of back substituting. So here, the equivalent system will be, so remember our unknowns were the A's, right? So we'll have 1A0 plus 1A1 plus 1A2 is equal to 8. The second one, the first part zeroes out, and we'll have 1A2 plus, 1A1 plus 4A2 is equal to 9. And then our last row will be that A2 is equal to 2. So, back substituting, what will happen? Well, here we go. We still have our A0 plus A1 plus A2 is 8. But if I back substitute A2 into the second row, equal to 2 into the second row, I'll have A1 plus 4 times 2 is equal to 9, right? And then we'll end up with what? A1 will be 1, I believe. And we still have that A2 is 2. And then when I back substitute in this first one, A0 is what we'd be solving for. A1 we got is 1. A2 is 2, and that's going to equal to 8. And so what does that give us? That's going to give us that A0 is 5, right? And then, of course, we still have our A1 is 1, and A2 is 2. So putting that back into the form of the polynomial, what's going to happen? Our polynomial in X, do a brighter color here, our polynomial in X, then, from this information here, is going to be what? Well, remember it was A0 plus A1X plus a2x squared, right? And so our polynomial in x will be a0 was 5, a1 is 1, so we'll just have plus x, and a2 is 2, so we'll have 2x squared. And we're done. Cool, cool? All right. So the polynomial that that fit these 3 points turned out to be a quadratic that opens upward, right? Now let's take a look at another application called network analysis, right? So networks composed of branches and junctions are used as models in fields like economics, traffic analysis, electrical engineering, many more areas too. So in an electrical network model, you use something called Kirchhoff's laws, I'm sorry if I'm mispronouncing that, to find the system of equations. So Kirchhoff's laws basically say that, number one, for junctions, all the current that flows into a junction must flow out, and paths, so the sum of all the IR terms, where I denotes current and R denotes resistance, in any direction around a closed path is equal to the total voltage in the path in that direction. Okay? So let's kind of trace, where these are going, the paths and, all this good stuff. So here, by the way, the constant numbers here, they're in ohms. So they're in ohms or volts. Okay, so this here is like 3 ohms. And 17, this will be 17 volts. This is 9 volts. And then we've got 2 ohms. And this is 1 ohm. Okay? Okay, let's also get kind of some labels for these paths. Okay? And so if I name this one here A, and then right here, this will be B, and then C could be is going to be right here, and then D is this part here, and that'll help us, traverse around this this thing. Okay, so in this one, we have 2 paths and we have 1 current, right? So here, I just copied this image so that it wouldn't get too messy. So if I start out and if I look at path A, B, C, D, A, that's the easiest one to visualize, right? So what happens here? It starts here, right, at A, and then moves here to that 1 ohm, right? And it's heading this direction. And then it goes through B, through going along I3 here to this 2nd ohms, right? And then this is all still I3, and then it goes up to D, and then curves around through I1 and back to A. Cool, cool? So that path is going to be what? Remember that you're doing your IR, right, terms. So I is current and R is resistance. So we've got this ohm here, right, multiplies to I1. So we have 1 I1. And then what happens as we go from B along here, I3, do you see we hit the 2 ohms, right? So it'll be plus 2 I3. And then that goes along until we get back to our I1. And that, so we remember we traced it along, and then look, it ended up at the 9 volts. So these are the voltages we used. If we look at path notice there's that middle path as well. So I'll do it on the one to the right of the first image. So if I start at B, if I go from B over through C, I get to my 2 ohms, right? So path started at B, went to C. I've got my 2 ohms, so I'll have 2 I3s. Cool so far. And then we keep going around. We get to D and turn the corner. And then you see I've got 17 volts there. So when I finish this, it's going to be equal to the voltage, all right? But what's happening, we're going to hit up another ohm. So here, do you see how we get our 3, we have our 3 ohms. And then it ends up back at B. So that's along I2. And then, sorry, we don't need the unit there. So that's the second one. Now, what do we know? We know that if we just look at the I's themselves without the ohms, right, we'll get our total current. So, you know, the addition of the 2 currents, I1 and I2, do you see they both feed into I3, right? And what goes in must come out, right? So in that one, this is what I'm looking at. So I1 is going this direction, right? And it's got to go all the way along, and it keeps going this way. Sorry, I don't want to go that far. And it feeds in to I3, okay? So all of that is going to be, all of our I1 stuff is going to feed into I3. All of this stuff, okay? Now, all of the I2, do you see the I2 is going this way along here, and that's going into I3, right? So if all that's going into I3, then the sum of it has to equal I3. Make sense? Right? That's going to give us I1 plus I2 equals I3. So now we have 3 equations, right? And 3 unknowns. So let's put this into a system and go ahead and solve it, right? So here we go. Our system is going to look like what? We'll have I1 plus 2I3 equals 9. And then I'll put these in order. We'll have 3I2 from, this is path, sorry I didn't complete the path, did I? This was path B, C, D, B. The second image we did. And then our current was that one. And then, so we have 3I2 plus 2I3 has to equal to 17. And then for the current part of it, we just have I1 plus I2. I'm going to have minus I3, and that's going to equal to 0. So I'm just writing it as a system, right? And these will be, by the way, in amperes. Okay, so at the end we'll have a capital A for ampere. Now, with this one, this would be maybe a good time to show you how to use the graphing calculator. So I'm going to go ahead and use the app to show you this. It's a really great app. It has, for the most part, the same, the same setup. It has drop-down menus as opposed to scrolling down when you use the actual calculator, but it's pretty good. So to find the reduced row echelon form of a matrix, this is what we do. We need to go into matrix. So it's in the second menu under that X inverse key. And so when we do that, you want to go to edit, because we have to enter the matrix in. And then I'm just going to pick matrix A to edit. And so we want to have the number, enter in the number of rows. So the number of rows, what do we have? We have a matrix that is a 3 by 4, right? And then we just enter each of them in. So the matrix is going to be what? 1, 0, 2, 9. For the second row, we had our path B, C, D, B. So we'll have 0, and then we had 3 I2s, and we had 2 I3s. And then what was the voltage? 17. And then with the current was the last one we did. So 1, 1, -1, and 0. Cool, cool? All right. So once you've got that done, you quit out of the edit menu, right? So here, just second quit takes you out. Now we want to go back into the matrix menu. Now we're going to do math on our matrix. So there's all these things you're going to have to, scroll down on your calculator. I want RREF, so I'm going to pick RREF. And now what you do is you go back into the matrices, and you got to pick which matrix. So the one we edited matrix A, and then enter, and this is our reduced row echelon form. Isn't that groovy? A little bit easier than doing it by hand, huh? All right, so in 1.1, by the way, my last video I did, I showed you how to use Octave, which is the free version of MATLAB. And so now you know how to do it using the graphing calculator. Corresponding matrix to this was 1, 0, 2, 9, 0, 3, 2, 17, 1, 1, -1, 0. It's augmented. And that row reduced to, using the calculator as we did, to 1, 0, 0, 1, 0, 1, 0, 3, and 0, 0, 1, 4, which translates to I1 is equal to 1, and we're in amperes. I2 is equal to 3 amperes, and I3 is equal to 4 amperes. And that is our result. Cool, cool? All right. So I put screenshots of everything. Hopefully that explains it well enough for you. If not, there's a ton of stuff on YouTube that you can utilize. And this brings us to a traffic example, right? So again, I'm going to name the junctions here. Wherever there's like an intersection, right? So I'm going to name the junctions just to make it easy to see, navigate. All right, so remember, what flows in has to flow out, and this is how you can figure everything out. So into junction A, right, what do we have going on? We've got 400 flows in, right? X2 flows in to A. But what flows out of A? Awesome. X1. So this is what I did for this one. So we had 400 going in. X2 is going in. But going out, we have X1 for that. Cool? All right, so next up, let's see, let's do junction B. So flowing into junction B is X1, right? We also have X3 flowing in. And so here, X1's flowing in. X3 is flowing in. And what's flowing out? Beautiful. 600's flowing out. And X4, right, is also flowing out. Cool? Okay, so now let's look at junction C. So flowing in to junction C is X4, right? We also have X5 flowing in. And I think that's it. And so what's flowing out is the 100. And then now let's look at junction D. So junction D, 300's flowing in, right? But everything else is flowing out. So we'd have, I'll just say equals 300. And then flowing out is X2, X3, and X5. So X2 plus X3 plus X5 is flowing out of there. So let's clean it up a little, make it look pretty, right? I'll go ahead and have the constants be positive when I manipulate these. So we have equals 400, and then this will be X1 minus X2. Right. So then the second one, the 600's already on the other side, so we'll have X1 plus X3 minus X4 equals 600, and then we'll have X4 plus X5 equals to 100. And then our last one will be X2 plus X3 plus X5 is equal to 300. Cool? So to solve the system, again, on something like this, why don't we go ahead and take a look at the technology? All right, so I'll go through much quicker next time on the technology, but the matrix that'll correspond to it will be 1, -1, 0, 0, 0, 400, 1, 0, 1, negative 1, 0, and then 600, 0, 0, 0, 1, 1, 100, and then the last line will be 0, 1, 1, 0, 1, 300. Okay, so now let's see what this row reduces to. I'll show you something really cool as well. I'm going to row reduce the same letter name matrix, but I'll just edit that one. So I'm going to hit second X inverse to get to the matrix menu. Remember, you got to select edit on the top menu, and then I'm going to edit the same one we worked with. So now this time we have a 4 by 6. We have 6 columns with the augmented matrix. So 1, negative 1, 0, 0, 0, and then 400. The second row is 1, 0, 1. Negative 1. And then 600, or no, 0, sorry. And then 600. And then our third row, 0, 0, 0, 1, 1, and then 100. And our last row, 0, 1, 1, 0, 1, 300. So remember, what do we do now? Beautiful. Second quit. This is the cool part. If you hit second entry, it brings up the command from last time. So we've edited matrix A. So this saves you from having to go back into the matrix menu, which I think is cool. So this is our matrix here. So notice that we've got a dependent system. Okay, so now we've got our reduced row echelon form. So here again, I mean, we can just go ahead, we can write it in, but I'm sorry. We can write it in, but it's right here, right? So, okay, what does that correspond to? I mean, this corresponds to the system x1 plus x3 plus x5 is 700. x2 plus x3 plus x5 is 300. And then x4 plus x5 is 100. And we don't need that bottom row of zeros, right, in our system. So here, okay, well, what does that mean? I mean, why don't we go ahead and take a look? We don't have to find official parameters because we're going to be told what to plug in on the left here, but we might as well isolate stuff. So x1 would be equal to 700 minus x3 minus x5. x2 would equal to 300 minus x3 minus x5, and x4 is going to equal to 100 minus x5, right? So notice that x1, 2, and 4 are all in terms of x3 and or x5. So, all right, find the traffic flow when x3 is 0 and x5 is 100. So, all right, we just need to plug it in, right? So the traffic flow in this case will be, well, x1 would equal to what? 700 minus 0 minus 100, which is 600. x2 will equal to 300 minus 0 minus 100, which is 200. x3 will be 0. x4 is, because that was given, going to be 100 minus 100, which is 0. And x5 is 100. So what I was doing is plugging in wherever there was an x3, actually, back here, wherever there was an x3, I plugged in 0. So that's why I had these. And then wherever there was an x5, I plugged in 100. And so that's our traffic flow for that situation, all right? Find the traffic flow when x3 equals x5 equals 100. So we'd have x1 equals 700 minus 100 minus 100 would be 500. x2 is 300 minus 100 minus 100, which is 100. x3 is now 100. x4 will be the same thing, right? 100 minus 100 is still 0. And x5 equals 100. So just imagine, playing around with these things. Like, I don't know if you've noticed, but all the work they're doing on the 5 and, closing lanes, reducing the speed of traffic and that kind of stuff. It's real interesting. And they use matrices, for planning to solve these systems. So it's actually something we sure can visualize living in Southern California. All right, so that is another application of how you can use matrices. So this takes us to the next section, so we're all set for today. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, please subscribe. Bye.